welcome everyone to this first of many, what hopefully will be really fantastic talks in this fall showcase for Planet Texas 2050. For those of you who haven't yet met me or seen me on Zoom, my name is Dave Kramer and I'm the program director for Planet Texas 2050. I started in April, so my entire Planet Texas existence so far has been just like this. So this feels great over Zoom and virtual, but thank you so much for attending. I like to have visual aids in person, so I just wanted to display this off my desk. I really do believe this, that what starts here changes the world, and it's something we try to live up to at PT 2050, thinking about how the work that folks like our presenters today will be presenting is not only helpful for us internally at UT, but across communities, in communities across Texas, and certainly beyond, the being relevant and helpful for communities globally, and to help deal with the effects of climate change, make more resilient communities, and prepare us all. So today we have two fantastic presentations, one titled From Rain Forecasts to Stream Flow to Flood Modeling with Paola Passalacqua, David Arcter, Harry Evans, and Jing Zhen. I apologize if I've gotten any names wrong in my pronunciation, and Suzanne Pierce and Daniel Hardesty Lewis from TAC. And then the second presentation is the title is Strategic Evacuation for Hurricanes and Other Regional Events with and Without Autonomous Vehicles. And so we have Jooyong Lee, Krishna Kumar, and Kara Kockelman involved with that. With that, I don't want to take any more time, but I just need to mention logistics. Jonathan Lowell and I will be managing the chat, the questions that folks have. So if you have any questions, you're welcome to raise your hand or pop them in the chat box. Given that it's just Zoom, it's not a webinar, there's no Q&A, so just use the chat. And presenters, as you go along, let folks know how you want to manage Q&A at the end or peppered throughout your talk, whatever works best for your flow. So, Jonathan, would you like to add anything else, or are we good to go?
No, I think we're good. I think Jooyong will go first, and then there might be a few minutes in between for Q&A before Paola, and then we can maybe merge the two Q&A after. And then I think a few of us can stick around. We don't have a hard stop at 1, so if people do want to stick around longer and ask questions and discuss, you know, we can be here for a little bit longer. So yeah, just FYI, and take it away, Jooyong.
Yes, hello, I'm Jooyong, and I'm going to share my screens. Yes, so here it is. So nice to meet you. I am Jooyong Lee, and this is the presentation of the paper titled Strategic Evacuation for Hurricanes and Other Regional Events with and Without Autonomous Vehicles. So to start on with the background first, usually what I'm going to study in my study area is solving the transportation assignment problem. It's generally asking the answers to the questions like who goes from where to where and how many of them are there at what time. And usually what we assume in that kind of questions is that there will be a travel demand data given from like a survey results or food survey, but evacuation is a very rare event, so that kind of data set is not well established, so that we have to first think of a model estimate that can give some realistic demand results. And as a general statement of the evacuation, well-timed and directed evacuation is important, since the time needed to evacuate everyone, if that time is too short, that can lead to an internal gridlock effect, because everyone will be concentrated at a short period of time, so that there will be a severe congestion and takes a long travel time for everyone to evacuate. But if the time duration was given too long, that means someone departed too early, but someone departed too late. And that will result in inefficient evacuation. So the balance between these two are needed to facilitate the evacuation. And in this specific research topic, I'm going to assume there will be privately owned autonomous vehicles to facilitate the evacuation. So the autonomous vehicles are like a perfect form of Tesla, for example, that is self-driving without the driver. It's like a machine and computer that performs more efficiently than the human drivers. So this is the network design and evacuation, and it's a logo that I was using for our PT 2050 project. So the study area is the Houston-Galveston 8 counties, as shown below. And this is the link and node map of the study area. So the link is like a road segment, while the node is the point where the links meet. So it's like an intersection. And this is how my study area looks like. And we can, there's like a traffic analysis zone, which is made up of several links and nodes, so that this study area is first defined in each traffic analysis zones, and then each zone has links and nodes inside in it. So the settings that I'm going to use, it's a simulation-based study. And from the population data, we can see that we can estimate there will be 6 million persons, so that there will be 2 million households. And from the vehicle ownership data, we have concluded that there will be 4.4 million vehicles across the 8-county region in Houston and Galveston. And the numbers of links and nodes and TAZs are as shown here. And then once we have estimated the total amount of vehicles in these 8 counties, then we have to estimate how many vehicles will be in each TAZ. So it's an assumption based on that the TAZs, each TAZ's total vehicles will be proportional to the number of person trips originating in that TAZ. This is the result from a survey result that was provided from the local metropolitan organization. And then random link inside that TAZ will be randomly chosen as the origin of each household's vehicles. And I've only sampled 0.1% household vehicle due to the computing power limits. And this is the evacuation algorithm that I'm going to use for the results that I've got. So I'm using a tool, simulation tool named SUMO, which stands for Simulation of Urban Mobility. It's an open source software that simulates mesoscopic vehicle traffic flow, but it can track each individual vehicles so that it's sort of an agent-based model. And it not only performs the traffic flow simulation, but also it reflects the destination choice and route choice using the application programming interface named Tracy. And to do this, A-star shortest path algorithm was used, which was, these two are the default settings that was provided from the simulator. And as I said, this is the sampling size. And I've used the TAX Stampede 2 supercomputer that we have in the UT Austin to optimize the departure times and destinations of the evacuating vehicles. So since this is posing the evacuation problem by equations, we need variables that's needed in the equation. So the first variable is the departure duration. This is the time from the first to the last departure of the evacuating vehicles. And then the second variable is the departure time schedule, which is the proportion of the vehicles departing in each time interval t, where I assume there will be 5 intervals within this t duration. And then the vehicle share departing at each interval is namely pi, where I is from 1 to 5. And then in each simulation time step in the simulator, vehicles will be departing based on a Poisson random number generator within each time interval to follow the PNT plan that I've posed above. And since it's simulating evacuation, we need a disaster for the evacuees to depart. And the disaster case comes from the Hurricane Harvey flood data on the date August 27th, 2017. So this is the date when the flood started in this region and then became severe problem in the early September. So this data provides when someone's house flooded and how deep the flood depth was. So based on this data, we can estimate when someone's house flooded so that he had to evacuate, how deep the flood depth was so that we can prioritize those who have more severe damage compared to those having relatively light damage. And as an assumption, I've assumed there will be 10 shelters. They are the high schools located outside of the Texas Beltway 8 road network. So they are outside of the downtown. And the definition of evacuation is the arrival at one of the shelters. And each shelter has the capacity assumption where it is like the demand over 10. So theoretically, everyone can be evacuated to one of the shelters. But the lower the volume to capacity ratio is, the higher the probability to be chosen as the destination for the 10 shelters. So this means, so the volume to capacity ratio means the rate of the seats left compared to the total seats available. So if there's still seats left, it's more attractive destination compared to the shelters that has few seats left. And this is how the evacuation timing can be posed with two hypothetical evacuees, namely 1 and 2. And for evacuee 1's case, let's say this is the time when his house flooded, and this is the departure when he left his house. So his case is a late departure case. And then this will be the travel time from the departure until arrival. But for evacuee 2, he was a little bit cautious than evacuee 1. So he departed earlier than the flood happened. And this will be the travel time to, so in all cases, there will be 3 variables that we have to think of: the late departure or the early departure, and the travel time needed from the departure until the arrival to at one of the 10 shelters. So yes, it's a little bit difficult, but it's easy. You can pose the objective, the cost that one have to spend as the sum of the travel time and the late or early departure time cost. So basically it's the sum of these two or these two. And then we're going to find out the P&T combination that can minimize the average evacuation cost for all vehicles. And as I said, there are autonomous vehicles assumptions, and they are hypothetical and theoretical assumptions, yet since we do not have those vehicles on the roads yet, but this is how the network will perform with more autonomous vehicles on the road. So this is autonomous vehicle 0 case, where every vehicle is human driven as it is right now, while this is all vehicles are fully autonomous vehicles. And the improvements can be made with more autonomous vehicles because at a given density, so that density is the number of vehicles per mile of roads. At a given density, the flow can be increased with more autonomous vehicles on the roads. And this is due to the fact that AVs are assumed to have shorter reaction time than human drivers because they are computers, so they can understand what's happening on the roads better, and then they can perform their action more faster than the human drivers. And for different scenarios of autonomous vehicle penetration rate, I'm using 3 types of scenarios where there's 0 autonomous vehicles. So it's business as usual case, and this is half and half, and this is fully AV penetration rate scenario. So yes, this is the total algorithm that I've explained so far. And to perform this algorithm, genetic algorithm method is used with the parameter settings as below. So this is the simulation results that will be coming up. So this is the optimization results for different scenarios. So this is the autonomous vehicle 100% case, while this is autonomous vehicle 0% case. And as this result shows, this is the evacuation cost by iterating the algorithm until the minimization was achieved. We can see that AV 100% case has lower cost compared to AV 0% case, so that we can say the evacuation will be improved with more autonomous vehicles due to the better vehicle performance. And this is the specific result of different AV scenarios. It's the departure and arrival curve by time, and this is the vehicle count. So when everyone departed, the time at this point is the variable t, and the shape of this departure curve is defined by the variable p. And then from the departure until the arrival was simulated using the traffic simulator Sumo. And this is the result of the p and t variables after iterating the algorithm for the 3 different scenarios. And we can see that the first time slot was heavily used. So there's an initial large peak at the first interval for everyone to evacuate as soon as possible. And then the shape changes until everyone finishes their evacuation. So for the p variable, the first time slot was heavily used, but the t variable was not that much sensitive to the AV penetration rate. But as we have seen in the previous slide, the evacuation costs were sensitive to AV rate. So these were studied in more detail, as shown here. So this is a kernel density estimate. So it's basically a curve fitting result of the histogram. And it's for the left figure is for evacuation cost, and it's for the right is the travel time. And from the average value, based on AV scenarios, we can see that the cost and travel time decreases. And also, since it's the histogram, and AV scenario has more portion in the lower evacuation cost section, so we can say that AVs deliver lower travel times and cost, so that much less uncertainty can be expected in the order following, and this enables more efficient and safe and reliable evacuation. But one thing to mention about the travel time is that the AV evacuees have shorter travel time so that they can avoid the evolving flood threats while they are traveling, which is also an improvement compared to the business as usual case. And these improvements comes from the low congestion. So having low traffic jam on the roads. And this is the congestion index of the actual travel time that the vehicle spent from its origin to the destination over the hypothetical time as if the vehicle traveled at the speed limit. So if this ratio was small, it means the vehicle was traveling at speed limit. There was no congestion, while having a large congestion index means there was a severe traffic jam. And since AVs have lower congestion index, AV evacuation improvements comes from low congestion rates. And the right figure is the result of the clearance time. This is the time until every evacuee reached to the shelter, so that the time when the last evacuee reached to one of the shelters, so that there are no more vehicles left in the network. And I've repeated the same simulation 5 times to see the average performance. And we can see the tendency that the clearance time decreases with more AVs on the network. But one problem we still have is that even in the best case, we still have to spend 3 to 4 days to finish the evacuation. Even if we have like the fully perfectly performing autonomous vehicles on the roads, we still have to spend 3 to 4 days to evacuate everyone. So it's a little bit problematic yet. And yes, lastly, this is the scenario analysis. It's the perfect case result with the PNT combination for the human-driven vehicles only case. And the second and third column is the early departure scenario. So this one is where everyone is panicking and leaving at the first interval. So there's a huge concentration of vehicles in the network. And the second one and the third one is there was shorter time duration given for everyone to evacuate compared to the optimal case. So these two represents early departures. And this reduces the clearance time, which is natural because everyone departed early. That leads to everyone arriving earlier. So it can reduce the clearance time. But since there's huge vehicle concentration in the network, this adds more congestion compared to the optimal case. And then result increases the average cost per vehicle. So it's not good to have early departures. And the fourth column is the late departure case. So this means someone departed very late compared to the optimal case. And that means the departure time is sparsely distributed over the time. So this enables less congestion and lower travel times because there's low vehicle congestion, but increases the clearance time because someone departed very late. And in result, this also has higher evacuation cost compared to the optimal scenario. So this scenario analysis shows that the optimal combination of the variables that I've defined in the equation is important by changing the variables in each scenarios. So current conclusions so far I have are that departure time, schedule, and duration are sensitive to the disaster's arrival, but they were not that much sensitive to the AV penetration rate. But still, AVs deliver better evacuation performance due to the better vehicle performance. And from the scenario analysis, the optimal combination of the variables that I've defined in the problem was essential in improving the evacuation performance. But still, the problem that we're still facing is that evacuating everyone takes 3 to 4 days. And the evacuees have to spend 10 hours to 13 hours traveling on the road. So this is still problematic. So we have to do something more than having just perfect Tesla on the roads. So the future topics that I'm improving this to have better evacuation performance is by introducing high occupancy vehicles like the bus operation in temporal pickup stations so that people can use high occupancy vehicles, and that will lead to lower congestion and higher system benefits. And the final solution that I'm proposing is the dynamic ride sharing. So it's like an Uber pool operating autonomous vehicle. So in this case, the autonomous vehicle will be going to your household and pick you, and then going to the other household and pick them until the seats are full, and then we'll evacuate. So it's a high occupancy vehicle, but provides door-to-door service. So it's better for the evacuee because it can wait at home safely. So these are the results that I've prepared for this presentation and was done throughout the PD 2050 project. And I would be happy to have any questions or suggestions today. Yeah, thank you very much.
Looks like Joshua has a question. Feel free to unmute and go for it.
That was my reaction emoji. It's like the clapping one.
Jooyong, can you take your screen down?
Yes, sure.
Yeah. Cool. We have a minute or two for a question before Paola, if anyone has a question.
Hello, hi.
Yeah, go ahead.
This is Ashutosh. I have one question. So firstly, thank you. It was a great presentation. And my first question is that, you have simulated the behavior of AV vehicles. So were those AV vehicles trained on some data, or is it that Sumo directly provides you with trained agents that you can directly use for your analysis?
Sure. Yes. I think I have to share my screen again to
Sure, go
explain
ahead.
that. Yes.
Yeah.
Let me see. There it was. Yes. So it comes from this result where it was based on previous research results. So basically, this is the shape of how this is called a flow and density relationship as a function. So this means that if there are more and more vehicles on the road, so if the density increases, there will be more and more vehicles flowing out of the road. But at some certain point, so this point is the capacity, then there will be more and more vehicles, so the density will increase, but the flow will decrease so that we can experience the traffic jam at this moment. That's how the road network works. If there's more and more vehicles, there will be more and more vehicles going out, that until at some point where it reaches the capacity, and then still there will be more and more vehicles until every vehicle is located bumper to bumper. This is the bumper to bumper point where no one can go out. So there's traffic jam growing. And from this relationship, by using different shorter reaction time for autonomous vehicles and human drivers, we've calculated the different shapes of these functions under different AV penetration rates, and then use this traffic flow results in the simulator tool to represent it as an autonomous vehicle 0% case or 50% case or 100% case. So that's how AV simulation was performed in this result.
Okay. So the AV behavior is modeled using a shorter reaction time.
Yes,
like
generally having shorter reaction time.
So you give that as an input to the simulator, and it generates agent like vehicles that behave with a shorter reaction time, and those are treated as AV vehicles, right?
Yes.
And my second question is that when we are doing these rescue operations, do we assume that all these AV vehicles, are they operating according to some central agent, like how they should route and move, or do they have their own individual policies?
Yes, that's a very good question, because that was not yet solved. So that's why I was assuming they're privately owned autonomous vehicles. So the driver, so in this case, it's not the driver, it's the rider who plug in the destination, and then this vehicle goes at the choice of the rider. But that's in the future topic that we're still doing, where like this case, that will be what you were saying, because there will be a central management organization who will be ordering the movements, or like pick up him first because he is in more dangerous situation, or like pick up that or use that route because that is a better route. So that kind of central management operation is yet under development. Yes.
Okay, got it. Thank you.
Great. I guess, Paola, do you want to go ahead and start?
Yes, I will. All right. I think you see the slides, so we're all good. Awesome. Thanks for the thumbs up. I love those. Cool. All right. So first of all, thanks much for the invitation to present. And we're going to follow up still talking about hazards and flooding, possibly prior to that. So maybe we can reduce the amount of people that need to evacuate, or evacuate with more time, I guess. So, and as you see, there's a title, but there's a subtitle, which is essentially, how do we get inundation maps now, right? So not in hours, not in days or months or years. And we're going to talk about this because there's different ways of creating this product. And I think they all play a role depending on what your question is and what your time scale of need is. But we're going to focus on real-time tools. And so I'm the person that gets to speak, but there's a whole suite of people that are involved with this project. It's actually larger than the number of people that Dave initially mentioned, because the group of collaborators is growing. I have new students. We also have strong collaborations with Lamar, and there's a very nice group of stakeholders from Southeast Texas that we've been particularly in conversation with throughout this project. And TAC, of course, that has enabled most of what I'm going to show you. All right, so main issue here is something that you perhaps are aware of. We're largely missing information on where flooding is likely to happen. We could talk about this for a long time. There's counties that are not covered. Even when you have flood inundation mapping, for the most part, it will need to be updated. And that's because with new studies and new data, we know that our flows are changing, and that's also due to climate change. And so either you need to update them or they're missing. And also for the most part, and we're not going to get to this problem today, but most of the maps actually only account for one type of flooding. So that's another issue that we can discuss. So for the most part, we don't have a lot of information. And we saw that here for sure in the 2013 flood, 2015 floods, during Harvey, that there was complete lack of information of what was going to happen, right? And so lots of these lack of information for the people that are managing the emergency is what has motivated a lot of the work that you will see. So there's, as I was mentioning in the introduction, there's many ways in which you can do flood inundation mapping. There's several ingredients that all of these different ways share. You need some way of predicting flows. So you need a forecast, and that comes from an hydrological model, which you either run or is run by someone else and so forth. You need some information on the topography, because you need to know what terrain you have, and that is how the flows are routed once they are on the surface. You need the river network, of course, because that's the main structure that routes, at least for fluvial flooding and for pluvial that gets into the network. That's the transportation device, right, by which the water reaches other locations. And then you need some approach for mapping. And so each of these ingredients has its own, presentation in a sense. There's different approaches to go into modeling, different approaches that go into topography and terrain analysis, depending on the resolution, different ways in which you can analyze the network, and certainly different ways in which you can do mapping. The combination that you see here in this workflow is dedicated to enabling simple and fast mapping that can be done. It's co-developed and can be replicated by those that are managing the emergency. So this is not going to be fancy, high fidelity modeling. There's a space for that, which is more for the preparation or kind of mitigation afterwards of the effect. But we're talking about during the emergency, what can be done and what tools can we provide so that response can be more informed. And so in terms of hydrological models, so from the first ingredient that you saw, we actually use the predictions that come from the National Water Model. So there's NOAA behind this and many other groups. And the point is that this gives you a forecast of the flow over the 2.7 million reaches in the United States and Hawaii. So this comes at different time scales. So there's a short term, a medium term, and a long term forecast. So you can get a forecast up to 30 days in advance. Now, usually the most accurate one, we normally look at the short term, and that's produced every hour, and you have an idea of what's going to happen in the next 18 hours. All right, and then there's also an assimilation analysis product that embeds also field observations or observations and gauges. The point is that these gives us an hydrological prediction that we can just ingest into our inundation map. Now, that model is routed through the National Hydrography Dataset Network, which was traced at 30-meter resolution. So if you're not familiar with terrain data, usually comes, you can imagine, in pixels, right, in squares. And at that pixel location, you have one value of elevation. Now, 20 years ago, or even 15 years ago, very commonly, or even if you look at global scales, we're talking about 30-meter resolution. So that means that for a block of 30 by 30 meter, you have one value of elevation. Now, development of technology has really pushed this in the last decade, essentially, last 10, 15 years, and has exploded into what is called high resolution topography. So now you have various ways in which you can take terrain information from a plane, you know, for satellite, and you get information at a 1 meter scale and below. So we actually have super high resolution. So now the interesting thing is that, so that model, you have the hydrologic prediction, that predicts discharge, right? So you know what volume per time you're gonna see in the river. Now that discharge needs to be translated into a depth, right? So you need to know how high the water is gonna get in order for you then to do inundation map. Now the problem is that if your center line, so where this flows are routed is through a line that represents the river network, the problem is that because it was traced with coarser resolution data, is actually out of place. So you can see here, and if you stare at this image enough, you'll see there's locations where it does a decent job, but there's locations where the blue line, it's really off with respect to what we see as the channel signature on the terrain, okay? And that's just because it was traced on data that refers to coarser resolution, and thus is not as accurate as high resolution. So we need the center line though to be in the right place, because we need to know depth information, cross-section information in order for us to then get to inundation mapping from discharge. So we've spent some time on this, and I won't go through the method. We can talk about it if you're interested, but this is something that we created through time. There's 10 years of work behind this. And it's an approach that is you know, publicly available to essentially take these center line from the National Hydrography data set and retrace them. So we fix them. You can think of it that way. So we still get the model that talks to the channel network, but now we adjust the channel network in such a way that now accurately follows the terrain information, right? So now it's in the right place. And what's behind it? It's an approach that essentially minimizes a cost, all right? So you can think of it as a cost minimization approach in which we define certain characteristics or parameters that the river has to comply with, and then we get the path that satisfies those criteria. So the advantage of this, there's various things. You know, if you're familiar with terrain analysis, often with problems with bridges, roads, right, across the channel, this can do this process automatically. So it's a global minimization approach. All right, so you have the hydrological prediction, you have the center line, we fixed them, right? So now, what I wanted to also point out the fact that this, of course, requires a bunch of coding and a bunch of things. And this is where really the PT 2050 project comes into the picture, because as I mentioned, the code has existed for a while. This actually, the core of this method was my PhD dissertation. So that's a 2009 code that was coded in MATLAB. So MATLAB is not open source in itself, but we released all the codes and everything for free, and then added various pieces. We transitioned to Python in 2017, and then we integrated the inundation mapping as part of this initial code. So from GeoNet, which was the centerline retracing, we integrated the method to do flood inundation mapping in 2018, migrated everything into GitHub. And when I started this project, we had this code that worked, but it really needed to be scaled up. So it needed help to say, okay, so how do I go from this watershed to county level, to state level? And that's really where the PT 2050 project has been really helpful to scale up tools that we already had, but they needed to be able to operate faster and operate over larger spatial extents. So now, so you have the hydrological model, you have the center line, now we need to go to a depth, right? And so what we do is that we take these predictions, we build what is called a rating curve. This exists at all gauges, but this is actually synthetic, so it is created from our data. And this just is a tool that allows you from a given discharge to get a depth, right? So once you have this depth water level, then you can expand into the terrain and say, okay, so if I have this height, how far am I gonna go? What depth am I gonna experience at a given location? And so we do that with an approach that is pretty simple. It's called the height above nearest drainage. And what this does, imagine that your house is here and the river is here. And so all we say is, how high am I with respect to where the river is at? And that's what value of depth I'm gonna get inundated at this location. All right, so it just needs terrain information. It needs a discharge prediction, becomes a depth. That depth becomes a flood inundation prediction in terms of extent and in terms of depth. So, you know, we compare this with FEMA maps where they existed. The comparison is pretty good. We have compared it with high water marks. And of course, what you imagine is that these tools are real time, right? So this can be run for a county in the order of minutes. Now, these tools do not substitute the nicer high fidelity models, right? So it's not that you say, oh, we don't need those. The point is that a tool like this, because it depends on elevation data, is not going to do great. For example, if you start having an hydraulic structure, specific behavior of the water, it also doesn't give you water velocity. But what this is helpful for, and you see it in the next few slides, that A, you can use it real time, and B, it also gives you very fast result of a large spatial extent. And then you can say, oh, there's a lot of uncertainty here, or I don't trust the results here. So let me run a model, but the numerical models are much more expensive for time and data that you need. So you can just localize those efforts and say, I'm gonna run a model here, but I don't need a model over other areas where where these tools do a nice job. So how does this then reach out to the stakeholders? So first of all, and some of my team members are in this call, which is great. So first of all, we work directly with people that had experience with emergencies before. That's extremely helpful because in this scenario, we don't want to develop the fancy map and publish our papers and fight to get a millimeter scale accuracy, and then we create something super complicated and nobody's actually going to use. And there's space for that, but this is not the case here. So what this leads to is essentially an application that has been prototyped that can be used by emergency responders also on the ground, all right? So what you can see here, for example, these are maps that David Astor created, and they're just super cool. So I stole them with his permission. So you have aerial imagery. This is Onion Creek in South Travis County. And so then you can see this is how these digital elevation models, so this terrain data looks like. So the scale is in meters, and we'll show you where there's higher elevation and lower elevation. You can see clearly the features that earlier you couldn't see that much because there's all the urbanization that is happening. So then over this, we create this hand layer. So now we know at each of these locations how high they are with respect to the point they drain to, right? So we have a first estimate of what are the lowest points, essentially what are the points that are most subject to inundation. Again, this is inundation from the river, okay? So then we can talk about ways in which this can be expanded to coastal or over rainfall and so forth. So this essentially gives a contour map of the floodplain depth, right? Gives an idea of what inundation you're gonna be flooded, what the depths are gonna be flooded. Then here is the center line, which you see now is nice and traced. So this is the one where the national water model is adapted to. So it's routing on a less accurate center line as we saw, and then we adapted to this one. So then from this information, we can get flood inundation mapping. Now imagine that you can run this tool real time, but you can also run it many times and have a bunch of libraries available, right? So then if you're a first responder and you're on the ground, there's this prototype application that is called Pin to Flood. And what essentially happens is that if you're a first responder, this is during an emergency, you can drop in where you are, and based on, let's say you have any information that you see water right there, but the challenge is, if I see water at this location, where else is it gonna be? Where am I gonna expect to get flooded? And what is the extent of the event that I'm looking at, right? And so you can drop various locations, you can record the presence of water, and based on a library of inundation maps that are already being populated, then you can get a likely extent of what you're observing based on the observations that you have, right? So if I have observations here, then I'm gonna say, okay, if you're seeing water at that location, it's most likely that you're seeing water at these locations as well. And then coupled with this, there's information on addresses that can be impacted, so you can get a sense of which areas are most populated, which areas may be most at risk, and how essentially you're gonna direct those efforts to either evacuate or what type of vehicle you're gonna use to reach those locations. So this has been demonstrated with a variety of groups that you see there: NOAA, USGS, FEMA, the Texas Division of Emergency Management, the local fire district. So I think people are really excited about this. And as I said, one thing that we need to remember is that in Texas and in many other locations, flooding actually happens from a variety of reasons, not only fluvial. So we're now working on essentially expanding these maps in such a way that we can account for other types of flooding. But the nice thing is that there's a method development into scripts, and then these applications exist. And as we improve the maps, we can always integrate these maps into the application so that it always uses the most accurate information. And so there's this continuous interaction and exchange with stakeholders. As I said, we have people in our team that have experience with this, and particularly Harry Evans and Christine Keys. And there's also groups that are extremely active. So we work a lot with the Southeast Texas community and with Lamar University. So there's a whole collection of people organized under the Southeast Texas Flood Coordination Study that actually get together every month. And you see there's river authorities, and there's drainage districts and cities, and there's mayors, there's all sorts of people involved. And that's great, because this way we can keep continuous communication as to what tools are available, and how these maps are being developed, and what information they can provide in case of flooding. Okay, and I think this is it. So I wanted to keep it relatively short, so if people need to go at 1, we can still have a conversation. But big thank you, of course, for the opportunity, and to the whole team. And I'll be happy to address any question that you like. And if you want to see this, just go on GitHub and you can download all the tools.
Thank you, Paola. We have a question from Carrie Stevens. Looks like she needs to leave in a minute.
Yeah, what she has to say.
Yeah. I don't know if you see it here, but basically asking about flood factor.
Yeah, I actually don't see. Oh, there it is. There is the chat. Okay.
I can read the question just to.
Yeah, I'm reading it. There's a new mobile app available from this group. First Street Foundation. Yeah, we're aware of that. What's your opinion on the quality? Ooh, that's interesting. So I have not actually looked at the data myself. I know of people that have, and I think this is awesome. It's a great effort. And I think as with every other large scale application, the people that have done detailed modeling in certain areas, I've started seeing that there's inaccuracies. That's kind of to be expected. Yeah, I don't know. I haven't understood completely how it works because of the trademarking and everything that is associated with that. It's a step in the right direction, and certainly has put a lot of attention, I would say, to these tools and making things available, which I think it's great. The models behind it are really good, because there's the whole Bristol group, and so there's some very nice models behind. I think locally there will be some differences for sure, and this still needs hours. So I think the point is also that, I mean, this is available and you can get a sense of how the risk has changed at a given location. But of course, if I get a prediction now and I need to run the tool now, right? This is not the response, but this is helpful to have, because I really think that these problems are solved with a hierarchy of different tools, and you can just do the modeling when you can do the modeling, do these tools when you can do these tools, use the model to compare, and kind of like, optimize your resources and say, I really need a model here, but I don't need a model here. So I think there's space for me to everybody in this board. And I think what's good about what we do is that this is minutes. Is it perfect? No. But we can compare to the models and see, what can we get in this, just based on elevation data. But yeah, great question, Carrie.
Thanks so much, y'all.
Thanks. Good luck with your class. I noticed, Paola, you mentioned at the very end of your talk the need to find the right kind of transportation. Certainly, we had that with the earlier talk about autonomous vehicles. I don't know if there's any crossover, how you see that.
Yeah, I think so, absolutely, because I mean, I remember during Harvey, and I think Christine, Christine is still connected. Perhaps she has lived way more emergencies on the ground than I have. I mean, seeing what type of information they had. But what I saw when we were at TDEM during Harvey is that actually there wasn't any crossover with information on which roads are actually going to be closed. So it was like, emergency responders didn't know where the high ground was. So I think the information is somewhere there, but it's probably not being integrated in such a way that the emergency happens now, and based on that prediction, which roads are more likely to flood. And I see Christina is unmuted, so please go ahead.
Yeah, and I 100% agree. I mean, it's the same problem that we personally would run into if someone told us to evacuate. And it's, how do you get out? And when we say there's water, like from even the application that we're using right now, if we say that there's water on the road, is there 1 inch of water on the road, or is there 10 feet of water on the road? So, and then is it going to get flooded sooner? So yeah, it definitely, you are correct in the sense that I know all the information is out there somewhere. And if we had nothing to do and we could sit down and merge it all together and make this one perfect app, which would take us a little while to do, like years, it would be very helpful. And so I do like the fact that other groups are working on stuff, and hopefully we're going to be able to merge it all together. But we are starting with that one app where the public safety can drop a pin and see the polygon. Again, public safety doesn't do anything too different than you would. You wouldn't, look at you don't look at the weather and say, oh, it's raining outside, and not actually look outside. So they're going to do the same thing. They're going to look at this polygon being returned, and they're going to say, does this match what I'm seeing? But we want to go from there, but we need to get it in their hands. And so we're really thankful. I'm learning a lot on the data side of things. So it's been very interesting.
Yeah, so roads are part of what we look at. We actually have other connected projects. There's a new tech stack project that we have, and then David Maidman is the lead PI. There's a variety of us all involved, and there's going to be another 60 sensors placed at bridges over the state of Texas, in addition to the 20 that we already installed. So this will start providing, for example, every 15 minutes information on water level and velocity. So those, you can start seeing that if I have a warning, at some level, some threshold that I'm monitoring, and I can say, okay, as soon as you leave, as soon as you pass this level, or the velocity is higher than this, then I'm going to start marking these roads as roads that are going to be a high risk. So I think the more, there's data, and of course, a big thing is just having data that converges into the same space, especially during an emergency when you don't have the time to just go grab things from various resources.
Hola, Carlos here. Nice.
Hey, Carlos. Nice to see you.
Thank you for.
See your picture anyway.
I'll turn this on.
Yeah, it's like my students are like, do you want to turn it on? I'll see. I'm happy to see.
It shows a mountainside. Couple questions. Your DEM, is it? Are you getting rid of the? Because I'm imagining an urban environment, right? The LiDAR is gonna detect the elevation of the roof of the houses, right? Are you cleaning that up, or
Right. So great question. Yeah. As of now, we are working with the bare earth, so everything has been stripped from the landscape. However, we actually have a number of people actually in this call, and Fernanda and Patrick and others. So we wrote an NSF proposal to get to the point that, and we'll see what happens with that. But the idea is actually to add the layers of information and go from this level to actually have full 3D representation also buildings and things like that, and start getting that part integrated into the flood information mapping. Because if it's stripped of all, especially in urban landscapes, this is where these tools suffer the most, right? I mean, when I designed it, it was geomorphology in nice steep landscapes in California. What I have to worry about is channel heads and string networks, and there's no roads. Yes. Now, when you take that to an urban environment, it's flat, so gradients are really not helping that much. And there's all these buildings and things which will create flow paths themselves, right? Because you start having certain areas that are obstructed, and certain areas where the flows converge. So we need to get to that level. We're not there yet, but hopefully we'll get to that point.
And the other question was, I'm wondering, in terms of, are there efforts to validate this, and also thinking about maybe a lot of the flooding, especially not during the most extreme events, is also linked to obstructions, right? So places where water, right. and that's kind of, that could be random, right? Totally random.
Yeah.
So, just getting a sense of whether most of the flooding that actually occurs in the region, let's say Austin or something, right, is actually due to that, right? Just thinking also about not only immediate response, but also kind of preparing, right, like the creeks or bridges, or the design and the maintenance of the drainage system.
Yeah, I think there's a variety of things that go into, they go into this. And I would say in some cases, for example, if you have hydraulic structures and things like that, you definitely need a model. I mean, we still have to demonstrate that, but I think as we get closer to the coast and as we are near bridges or near structures, I think there's some domain within which you actually need a more accurate model to do this. And we're doing with part of the NOAA project that we have that we didn't talk about, we're actually creating data for 7 counties, and we are doing a validation, comparison across resolutions and seeing where the method is more applicable than not. So locally, I think models will certainly be there. Models should be leveraged, particularly at local scales. But in terms of the mechanisms of flooding, so some of the work that we're doing now is, first of all, integrating information from terrain depressions. So starting to get information of where water from direct rainfall is going to accumulate and how to bring that into these maps. Because of course, if we look at Harvey, 50% of the area that was impacted in Houston wasn't even in the floodplain, right? So it was like just direct rainfall. And the other part that we're starting to think about is the coastal component, because again, events are going to be compound flooding, right? And most of the maps just do not account for that. So that needs to be combined, and it needs to be combined in such a way that is not incomprehensible when you're dealing with an emergency, because then we start thinking about uncertainty and it starts being to a level that might not be appropriate for when you're on the ground, but it will be appropriate when in preparation of future events, or as you're saying, in preparation and then mitigation afterwards. So I didn't really answer your question, Carlos, but
No, you didn't.
I think the point is that I never believe that no matter how great the method is or the model is, it's never the solution to all problems, and that's why I think there's space for these high fidelity models to run within hours or days. There's space for real time, perhaps less accurate methods that give you something to go by when you are dealing with an emergency. And I think all of this, if groups collaborate and integrate information, it should lead to better predictions, which is all that matters.
Yeah. No, thank you. Thank you.
Of course, it's nice to see you.
Yeah.
Well, a great presentation. I really enjoyed watching it. I think I really see the links, the going from 2D to 3D representation, and how that's important to really understand those flood predictions, because we need to consider the urban environment too. Yeah, yeah, but that's a really great presentation. And it's wonderful to see such a cross-disciplinary team too being part of this.
Yeah, it's been, it's really, I don't know what I would do without Christine and David Arctor and Harry Evans. Because, especially for a person trained in an academic environment that deals with computer things, I was in a couple of floods as a kid, but that's about it. But it does really, it always brings you back to the level where we need to operate, and it matters, before you get lost into, oh, I have these error bars, or I can push this and make it better. And it's like, all right, there's nothing, and you're making a tool available, and we're going to start from there. So it's always interesting. It's an interesting way of resetting kind of the question and the tool. And you can still strive towards the other one, but still provide solutions midway rather than, working on it forever and then maybe never reach out.
Absolutely. And I think that's the beauty of cross-disciplinary research, right? That's why we're all here and part of this bigger effort that is Planet Texas 2050. So thank you all. Thank you, team, and both presentations, actually. Really great work. And that really is these two are two example projects of what's to come for the next, and I'll pass it back on to Dave, but the next upcoming research presentations, which we'll do monthly now. But really cool. Thank you.
Thank you.
Thank you to everyone for attending, and Fernando, I think that's a great wrap up right there. So I think you put a fine point on it, and appreciate everyone coming out. Hope to see you next time. Jonathan, when is the next one that we have? I know we have one.
Yeah, so the next one is October 13th on a Tuesday, so roughly 2 weeks, and it will be Katie Brown, who I think has already left, but she was here, and
here.
Oh, you are still there. Sorry, Katie. That is right. It's the 13th. I think I have it memorized in my head, all of them, but yeah. And then it'll be Katie Brown and Michael Shensky on their Burkhold area environmental niche mapping project. and Anna Dabrowski from TAC on their digital object lifecycle project on sort of data management and data storage. So I hope to see you all there, and have a great rest of your day.
Thanks, everyone. Bye-bye.
Bye.